All right, 3.4 video notes. We dealt with perpendicular parallel lines in section 3.2. We're now jumping to section 3.4, which is perpendicular lines. Let me just go off the grid and explain what was in 3.3. We don't really feel like it's worthy of having a whole section, and I think I can kind of break it down to you. So I'm going to go off the grid here a little bit, if my board cooperates with me. All right, so basically, some things that we have from 3.2. Okay, we had a few theorems there. And one of the theorems says that if two lines are parallel, let's just say L is parallel to M. If two lines are parallel, then we knew that alternate, and maybe I need to write the word then in here, then alternate interior angles are congruent. That was one of our theorems. So, you have the conditional part. As long as two lines are parallel, then we can be sure that alternate interior angles are congruent. So over here to the side, I'll just draw a small diagram here to represent that. I'll add an extra set of arrows, transversal coming down, and so alternate interior angles were this angle right here and this angle right here. And so X and Y would be equal, or if we went the other way, A and B would also be equal because they are alternate interior angles. That's if and only if the lines are parallel. Okay. Now, the next one actually said if L is parallel to M, then alternate exterior angles were congruent. Okay, so moving back over to my diagram, the letters would change position, and it said as long as those two lines are parallel, then we know that X would equal Y and that A would equal B. So that's an example of alternate exterior angles. Okay, and then the third theorem basically said that if L was parallel to M, then, lose my end there, then, and the other one we had were same side interior angles are supplementary, or they add up to 180 degrees. So going over here to my diagram and readjusting, that would mean that X plus Y, they're not equal. X is an obtuse angle, Y is an acute angle, but they do add up to 180 degrees. Same thing with A and B. All right, so that was 3.2. Basically, all 3.3 does, 3.3 was pretty much simply the converse of all three of those above statements. We basically just switched the if and the then. They trade places. So they would basically read, if you have alternate interior angles congruent, then you have parallel lines, and so on and so forth. I'm not going to write all the rest of it out, but alternate exterior, if alternate exteriors are congruent, then L is parallel to M, and if same side interior are supplementary, then you can conclude L is parallel to M. So the whole point of 3.3 was these are ways to prove lines are parallel. That's pretty much all 3.3 is, and the examples are all very similar that we did in 3.2, so we didn't really feel like it was worthy of its own section. But this is important because on problems where we have to prove lines parallel, we can use all those angle relationships to do that. All right, let's go ahead and jump into the actual 3.4 and start dealing with some perpendicular lines. I've talked a little bit about the symbols beforehand, but we'll formally introduce them all right now. So perpendicular lines, the definition is they're lines that intersect at 90 degrees. We've been used to this little right angle here, so that's a symbol. If I want to show that two lines are perpendicular, for instance, line L perpendicular to M, I draw one line, call it L. The other line would have to come in at 90 degrees, M, and then I have to show somewhere that it's 90 degrees. Now, because that symbol means 90 degrees, and these two form a linear pair, have to add up to 180, you're 90 degrees. And then we can play vertical angles. And basically, when you have 190, all four have to be 90. There's really no other way to look at it. All right, let's move down to this next part where we define what a perpendicular bisector is. So if a line bisects a segment, okay, so that's our condition here. If a line bisects a segment, it divides the segment into two equal pieces. Okay. A perpendicular bisector of a segment, so this is what we're defining. A perpendicular bisector is a line that does two things. It's perpendicular and it goes through the midpoint. So it's a two-part criteria. Hence the name's got two parts, perpendicular bisector. So let's look at this example here. Looking at this example, I see that E is the midpoint, and I can tell that by these markings here. E's right in the middle. So CD is the piece that got chopped in half at 90 degrees. So this line right here, AB is the perpendicular bisector. Remember, this upside down T, this represents perpendicular. I'm not going to write the word perpendicular out too much. It's a long word, and when I have a nice beautiful little symbol here to use, I'm going to use that from now on. And I see the markings right there. Now both of those lines are perpendicular to each other, but CD is not a perpendicular bisector of AB because I don't have any markings here to show that AB got chopped in half. Okay, so that's a perpendicular bisector, and sometimes it could be on an angle. You could have a segment here, and if I want to draw a perpendicular bisector, I got to go right through the middle, and I have to do it at 90 degrees. So the blue line there is a perpendicular bisector. Alright, so example over here, PQ is a perpendicular bisector of RT, so I know that there's 90 degrees right here. RS is 4. Well, since PQ is a perpendicular bisector, this side 4 has to match this side, which would be 4. And I should now be able to fill in the following values. Well, number 1 says, what is the distance from S to T? Well, the distance from S to T is 4. What would the distance be from R to T? Well, R to T is the entire length, so it would be 4 plus 4, or 8. And what would be the measure of angle PST? PST is right here, and that is also going to be 90 degrees. So pretty easy example, no algebra, just knowing the idea of what it means to be a perpendicular bisector. Alright, scrolling down, this is very important. Really important issue that we're going to use throughout the rest of the course. So I'm going to put a star there. The shortest distance from a point to a line is the length of the segment that's perpendicular. Okay, and let me kind of explain this. Alright, we have a line here. Think about it being like maybe like a wall somewhere, and you're standing here at Y, and I want to run from point Y to that blue line as fast as possible. Well, there's a lot of different options I could run. I could run from Y to W and touch the wall, but I'm going way out of my way. I could also run from Y to X, which would be a little bit shorter, but not the fastest. The absolute fastest way to get from a point to a line is, and the kids always tell me, oh, run straight to it. Well, both of these lines are straight to it, because all lines are straight, but run at it perpendicular at 90 degrees. That's the shortest distance. So if I kind of draw some other line, and I'm like way down here, and I'm going to say, hey, what's the fastest way? What's the shortest, fastest way to get from that point to that line? What you're going to need to do is you're going to need to run from that point to that line at a 90-degree angle. That's the important part. That's how I know it's the shortest distance. And I can set up algebra problems, I can set up inequalities to tell me that some distance is shorter than another one. For instance, up here up above, the distance from y to z for sure is less than the distance from y to w. Okay, that's a longer distance. I also know that the distance from y to z is shorter than y to x. Okay, so that's important. The idea is the perpendicular segment is always going to be less than all the other segments. Okay, the perpendicular segment is the shortest. All right, so let's do an example with some letters in here. So I'm looking at this diagram. It says, how far is point M? How far is that point from line LQ or segment LQ? Well, I look at my diagram. The distance from M to LQ is defined as the shortest distance, so that would be 5. Name the shortest distance from point R to line LQ. Well, the shortest distance is always the perpendicular one. And to name that line, it's RN. Segment RN is the shortest distance. Now, write and solve an equality. This is the part that you're going to have to do on the quiz and on the test. So I'm going to kind of go over here and erase this just to give myself a little bit more room. So here's how this works. I look and I find x. Well, here's the expression with x. And that expression represents segment Rn, or the distance from R to N. I know that Rn is the shortest way to get from R to LQ, but they give me a couple other options. They tell me that this is a length from R to LQ, or R to LQ, but it's 17. So I know there's a relationship between these two expressions here. This one, x plus 3, has to be shorter or less than the distance from R to Q, which is 17. I know that, because we defined it earlier. This has to be the shorter distance. So now I just solve the equation. I subtract 3 from both sides, and I get x 14, and I leave my sign the same. So this is my answer. My symbol doesn't flip. Remember, the only time you need to flip your less than or greater than inequality symbols is if you multiply by a negative number, or if you divide by a negative number. Then you got to flip the sign. But right here, all I did was subtract. I just subtracted 3 from both sides. There was no multiplying or dividing, so I didn't have to flip the sign. Now, what this means is, what this answer represents is any number that satisfies this inequality. Any number that's smaller than 14 will make my diagram true. So for instance, 10, 11, 12, 13, 13.9999, all of those answers, anything smaller than 14 will make my picture true. If I pick a number bigger than 14, I have violated the definition of distance and the shortest distance. For instance, if I plugged 15 in here, that would tell me that this red line is 18 and this line is 17, and that violates our whole agreement. All right, moving on down. Let's look at a few more things here. We have some theorems. These 3 theorems all involve perpendicular lines. I'm going to just kind of go through them quickly. So here's a conditional statement. If 2 lines form a linear pair of congruent angles. Well, if you form a straight line and you are equal to each other, there's only one possibility. You both got to be 90 degrees. So the conclusion is the 2 lines are perpendicular. So if you have a linear pair of congruent angles, the lines have to be perpendicular. Now, these 2 are kind of similar, but they are both pretty important. So in the first one it says, in a plane, if a transversal is perpendicular to one of the parallel lines, then it's got to be perpendicular to the other. So what that means is, I have this line here, and I have this line here, and I know that they're parallel. I know those 2 are parallel. And then this line Q comes running through, and somehow I'm given, or I can prove that it's perpendicular to this line. What I can then conclude from the theorem is, oh, it must be perpendicular to the other line, because there's no way for it to change course. And basically, because of parallel lines, all corresponding angles have to be the same. So all those 90s up above have to be 90 down below. And then the second one here, very similar, except for now we do not know. If you notice on our drawings, there are no arrows on these lines. So now we don't know the lines are parallel. I have two lines. They look parallel, but I don't know for sure. But I do have a transversal that's parallel to both of them. If you're parallel to both of them, then we know that R must be parallel to S. So this one is useful when you're trying to prove two lines parallel. You want to use this argument. If you want to prove two lines perpendicular, you're going to use this argument. All right, so let's move down and look at kind of a little, not really a proof, but just some examples of what can I conclude from the picture using the three theorems that we have up above. So I got this diagram. Right now, looking at the diagram, I can't assume anything. I can't assume anybody's parallel, anybody's perpendicular. I just have to look at the information given. So what if I'm given that angle 1 equals angle 2? Well, that would satisfy the first theorem up above. If 1 and 2 happen to be equal to each other, and they form a straight line, they're a linear pair, then I can conclude that the measure of angle 1 equals 90 degrees, which is also the measure of angle 2. And I also can conclude that really means that P is perpendicular to M. Okay, because if they're both 90 degrees, then P is perpendicular to M. Still don't know anything about N yet. All right, second part here. What if, so we get rid of that, what if the measure of angle 2 and the measure of angle 3 equal 90? What if somehow I know that you're 90 and you're 90? Well, then I know a couple things. Number one, I know that M has to be parallel to N, because that is their corresponding angles. Okay, but I also know I can use the theorem up above that said if a line is perpendicular to two lines, then those two lines must be parallel. So that's another way to know that the M and N have to be parallel to each other, because I have one transversal perpendicular to two different lines, therefore those two lines must be parallel. And then the final one, what if the measure of angle 2 is 90, and what if I have a set of parallel lines? Okay, I'm given these lines are parallel, I'm given that there's 90 degrees. Well, if you're a transversal and you're perpendicular to one of two parallel lines, you got to be perpendicular to the other. So I also know, let me get my letters back here, I also know now that P has to be perpendicular to N because of the theorem up above. All right, two quick examples, and then we'll wrap this joker up. This is the bulk of what your work is going to be like on your practice and on the quiz. So solve for each variable. Well, first of all, I'm given parallel lines, and I have a 90 degrees here. So basically, I know that every single angle on this picture is 90 degrees. All you guys are 90. Because if you're perpendicular to one line and the two lines are parallel, you're perpendicular to both. So now I just have to set up some algebra equations. Let's set this one up first. 2x has to be equal to 90 degrees. Divide both sides. I find out that x has to be 45 degrees. Then I'm going to focus my efforts over here. I know that the 3y minus 2x, that expression has to be equal to 90 degrees. But now I can use the fact that I know what x is. So I'm going to use the fact that I know x is 45. I just figured that out. And so I can plug it in to solve this next equation. 3y minus 90 equals 90. Be careful here. I'm going to add 90 to both sides. And I get 3y is 180. And divide both sides by 3. And I get y equals 60. So I think I've answered the question. I've solved for x and y. Now this is the one that people struggle with the most on the quiz and on the test last year. So the first thing is, it's an inequality. All right, it's an inequality, so it's going to be a less than or a greater than. It's not going to have an equal sign. All right, and I look up here and I have to look at the relationship, and the two pieces they're giving me this length is x, and then they're giving me this length, which is 2x minus 5. Now normally you can't just look at a diagram and say, oh, I think that line is shorter than this line. You have to have some other proof, and I have the proof right here. This 90-degree mark tells me that from this point to this line, that blue line there is the shortest distance. So I can set up my equation. X has to be less than 2x minus 5 because the perpendicular segment is always the shortest segment. And then I just go about solving this. I'm going to, a couple different ways I could do this. I think it might be easier to start off by adding 5 to both sides. I'll show you why here in a second. So that's 2x, x plus 5. Now I'm just going to subtract an x from both sides. And I get 5 is less than x. And using the symmetric property, I can flip that around. Same thing, I just like having the x on the left. So this basically says all numbers greater than 5 will make this picture true. All numbers less than 5 will make it false. And 5 will also make it false because there's no equal to bar there. And if I plug a number in, let's just pick a number greater than 5. Let's try 7, see if it makes the picture true. If I put 7 in here, and this is 2 times 7, which is 14, take away 5, that would be 9. Yeah, that's a valid picture. The blue segment should be shorter than the red one. If I were to pick a number 5 or less, the picture would be false. The red segment would be shorter than the blue segment. Alright, so those are the notes for 3.4. Hopefully you'll get those done tonight, and that way you'll have the entire block tomorrow to work on the practice. See ya!